The final talk for this session and for the conference actually would be by Miroslav Grmela, who was mentioned in the previous talk as well. And the title of his talk is Multi-Scale Thermodynamics, a Theory of Relations Among Mesoscopic Dynamical Models of Complex Systems. Go ahead.
Okay, can you hear me?
Yes.
Can you hear me?
Yes, yes, very well.
Okay, so good afternoon. I am...
Very first one, you can start.
Okay, so I'm starting. So let me first the notion of level of description. So I suggest you to think about hydrodynamics. So one makes some type of experimental observations, collects experience stimulates an insight. Then we are in the middle of 18th century. Euler, Bernoulli come, and hydrodynamics emerges. So that's one example of a level of description. We know that it's autonomous, of course, limited domain of applicability, and now if we have other levels of descriptions, like for example kinetic theory or completely microscopic, then we have a different amount of details. So these details, I will use the level of description with more detail as an upper level, and with less details lower level. I suggest to consider this passage from upper to lower as a kind of general kind of thermodynamics, and I will argue that this indeed includes the classical understanding of thermodynamics, and it is an invitation to use thermodynamics in microscopic physics and in other fields. So here are some examples of levels. Of course, the microscopic level is completely 10 to the power of 23 particles. Equilibrium, just volume, a number of moles. Energy are state variables. Hydrodynamic state variables are hydrodynamic fields. Kinetic theory, that's one particle distribution functions. And there are, of course, many examples in out of physics. And so we have some kind of, I would like to see it as a chain of levels, or say on the left are these more microscopic, this upper, and on the right the more macroscopic, less details. And so the some kind of extreme less details is D1 considered in equilibrium thermodynamics, where just the volume, number of moles, and energy, and say the level towards the most microscopic somehow doesn't have the end, because we can go to particles, quantum mechanics, quarks, I don't know. Yes, so that's a chain of levels. Thermodynamics, in a general sense, is a passage from upper level to lower level. In this passage, the details are lost, but the overall features are emerging. There is a gain involved. The upper time evolution, it means time evolution on the upper level, is in this passage is split into the reducing time evolution, or we can call it also emerging time evolution, and the time evolution on the lower level. Of course, in the case of lower level beam equilibrium level, there is no no reduced time evolution. So it means with lower level being equilibrium level, the passage is the reducing the upper time evolution is also reducing time evolution. Historically, Boltzmann was the first to formulate this passage. For him, upper level was the level of kinetic theory with one particle distribution function serving as state variable. Lower level, equilibrium level. Boltzmann equation governs the reducing time evolution. Details that are being discarded are details about the details of trajectories of particles undergoing binary collisions. In Gibbs Gibbs equilibrium statistic mechanics, the upper level is the microscopic level, lower level again is the equilibrium level. The reducing time evolution is not explicitly formulated. It is only in the past. It is only mechanics is just the where the upper time evolution enters. Where does the time evolution, microscopic time evolution, enter the Gibbs investigation? Conservation of energy and particles, and in the ergodicity of trajectories. What can we say in general about the reducing time evolution? So, as I said, it is the Boltzmann equation, yes, but now let's look for some kind of abstract Boltzmann equation. So it is some state variables which can be whatever, yes, derivative with respect to time, is some kind of gradient, dissipative part, and Hamiltonian part. Now, this in Boltzmann equation, this one is the collision operator, this one is the free flow. Yes, so but in abstract way, this what is a free flow is actually Hamiltonian. Actually, historically, in the context of hydrodynamics, this is the Euler part. This is a Navier-Stokes-Fourier part. The Euler part is Hamiltonian. This actually is very old result, 1850 from Clebsch. But only in 1968, Vladimir Arnold put it into some kind of formulation with Lie group and very general formulation, so it can be used in general. So there is the way of generally formulating Hamiltonian structure. As I said, basically started with Arnold, even though for Euler, the Hamiltonian nature of the Euler equation was recognized by Clebsch. Okay, so this is this part, gradient part, is in the abstract way is the Kahn, Hilliard, Landau terms, Ginzburg, Landau, but together. So this is, but now put together in the abstract form. The history goes back to 1980. I think for the first time it was done by Zaroshinsky, Volovic in one paper, and then in 83, 84 independently by Phil Morrison, Alan Kampfman. They thought about it rather in the context of plasma, and myself, and I sort of saw it in the context of complex fluid more. So that's the beginning. There is a kind of important and interesting observation that if we are on this chain of levels and we move towards this microscopic with more details, then the importance of this term grows and importance of this term. So the actually in the complete end of the microscopy, there is no gradient part. So this and it is important now, this cooperation between these two terms. So even, for example, in the, I will say specifically for the Boltzmann equation, in the Boltzmann equation, this part is a collision operator, and if this part if the Hamiltonian part is out, then this gradient part equals 0. Solution is the local equilibrium. It is a large space. However, the solutions to the Boltzmann equation, which also include this free flow term, reach complete equilibrium. So this free flow doesn't do anything to entropy, doesn't do any contribution to dissipation. It is completely permanent motion. But if put together with dissipation, however weak, enhances the dissipation. This is for the Boltzmann. I think this is very important and very general feature of these equations. For the Boltzmann equation, there actually exists a rigorous mathematical proof done by Cedric Villani, and he actually got Fields Medal for it. Some comment about the history of this viewpoint. So the Hamiltonian nature, for example, in hydrodynamics, the Hamiltonian part is the Euler part. Its Hamiltonian nature was recognized 1850 by Clebsch. So it's rather old result, but it was put into the form related to Lie group, and some kind of general formulation of it was made in 1968 by Vladimir and Arnold. So this is about the Hamiltonian part. Gradient part was those are results from 50s, basically 60s, by Kahn, Hilliard, or Ginzburg-Landau. Now putting together all on the Hamiltonian and gradient in some abstract way. First, it was made 1980 in the work of Zjaroshinsky and Volovic. And then in 1983, 1984, independently by Phil Morrison, Alan Kaufman, and myself. Now, solutions of this abstract Boltzmann equation, if we consider only initial and final state, it is that they are related by the actually, it is a Legendre transformation. It is maximum an entropy principle. The Legendre transformations are natural transformations in the contact geometry, and for this reason, contact geometry is a natural setting for geometry, for thermodynamics. And in fact, it is also possible to show that the solutions of that abstract Boltzmann equations are in fact is a continuous sequence of contact structure preserving transformations. It means Legendre transformations. Now, depending on what is the lower level, we have several types of this reduced reducing time evolution. So if the lower level is without time evolution as it is in equilibrium level. So that's the classical thermodynamics. In the case when the lower level is with time evolution, so it means, for example, we consider a passage from the kinetic theory to hydrodynamics. So hydrodynamics is the lower level. We can study the approach either as an approach to some quasi-invariant submanifold, or we can also consider the approach to the vector field on that quasi-invariant submanifold. So in the former case, it is again entropy that drives this time evolution. In the latter case, it is it's called rate entropy, which becomes, when the reducing time evolution is completed, becomes actually entropy production. So it means here we have this entropy, and entropy production arises in different types of reducing time evolution. So again, into chain of levels, we have micro and macro end. If we go towards micro, it's usually called extension. There is a gain and loss, gain of details or loss of overall. If we go right towards the macro, there is a loss of details and gain of overall features. And by going right from upper to lower, the entropy, the fact that we see the lower level inside something bigger, as emerged from something bigger, we are gaining, from mathematical point of view, we are gaining, in fact, geometry of that submanifold in that bigger space. And it is essentially, this is the entropy. This is the birth of entropy. So far, I have been taking examples only from physics, but there are, of course, levels of descriptions. So different descriptions with different amount of details, autonomous description with different of amount. There are many examples in biology, in social sciences, and in principle, this viewpoint I've been talking about applies here. In particular, we can think about big data. The reduction problem is the pattern recognition to extract some kind of essence, which we can see allegorically as some kind of natural conspiracy theory. Here are some recent references. In particular, I would like to point to you the recent book I have written with my colleagues Michal Pavelka and Václav Klika. It's in 2018, the Gruyter. It's called multi-scale thermodynamics. Since I believe I am one of the last or the last speaker, I am using this opportunity to thank the organizers, in particular Dr. Rampaulo. The thermodynamics, after the conference now, thermodynamics is enriched and its influence is enlarged.